All right. Ooh. Got it. Okay. All right. So good afternoon. I'm Julia Pagallo. It is my pleasure to introduce today's guest speaker, Enrico Santus. Enrico is Director of Artificial Intelligence and Machine Learning at Bayer. He obtained his PhD in computational linguistics at the Hong Kong Polytechnic University and worked as postdoc at the Singapore University of Technology and Design and at the MIT's Computer Science and Artificial Intelligence Lab. Enrico and I met several years ago, and we shared a passion for application of AI and in particular natural language processing. Today, these technologies power many of applications that everybody uses, like search, keyboard typing, intelligence assistance, voice recognition, and image recognition. As you know, AI is also present, very much present in medicine. Every day, there are new applications and explorations that happen in this field. And this field in particular presents many challenges and opportunities for researchers and applications. With a wealth of research and publications, Enrico is well positioned to take us on a journey about application of AI and natural language processing to medicine. Enrico has published over 50 papers on topics such lexical semantics, sentiment analysis, fake news detection, and information extraction for medical records. Enrico has also supported the creation of the Prayer, an interesting robot. It's a mouth-shaped robot that was exposed at the Pompidou Center in Paris in 2020. The robot speaks original prayers, which are generated by GPT-2 language models. These are large language models that were created by OpenAI researchers. In 2019, Enrico was invited to speak about natural language processing at the White House by the Record Management Office. He's the first author of a fact sheet about artificial intelligence for the American Congress. I'm sure you are as excited as I am to hear Enrico talk to us about the potential futures of AI and NLP in medicine. So please help me welcome Enrico to SDSU.
Thanks a lot. Really appreciate the invite, and thanks for a very wonderful introduction. I hope I can hold the level of the introduction. Let me share my screen. Please let me know when you see. I try to put it full screen. Let me know if you see it full screen.
Yes.
You do? Okay,
yes,
great.
We see it.
Great. Yeah. So thanks again for the invite. I'm very happy to be here, and I'd like to give you this presentation. But honestly, I also like to learn a lot from you. So I hope that this presentation is just the beginning for an exchange between us. So let me go through it. I will speak a little bit about the deep medicine, which is a framework that has been proposed recently by Eric Topol, who has been investigating AI in medicine for the last decade at least, if not longer. And he created this framework that is composed by three major steps. I will get into the steps. I will give you also some applications that I have implemented with my colleagues in a different moment of my career in medicine. And but I will start from an introduction about why do we need artificial intelligence in medicine. So Julia already said a lot about me, so I don't get any other information. Just that I got my PhD at Hong Kong Polytechnic University in 2016 in computational linguistics, and I'm currently director at Bayer. COVID-19, as you all know, has been a tragedy and a wake-up call for many of us. And the pandemic has tested multiple times the resilience of our healthcare systems. In 2021, it was actually the deadliest year in the US history. And later we will see a little bit more details on the numbers. But in general, like during 2021, over 3 million American citizens lost their lives. But the pandemic is actually only a tip of an iceberg that has been floating around for far too long. And I'm referring to the structural inefficiencies that are in what we may call the sicker system instead of healthcare system. Why? Because it takes care more of it takes more care about patients after they are sick rather than before they are sick, so when they're healthy. And there have been a lot of investigation about how the money in the healthcare systems are spent, and it has been found that there's a lot of waste, and this waste can amount to basically 30% of the healthcare spend, which is 750 billion US dollars. If we look at the major voices of waste, which account for 70% of the total waste, are the inefficiencies in care delivery, unnecessary services that are provided, and administrative inefficiencies. So why do we have this problem? Well, because the healthcare processes were actually conceived in the last century, when the knowledge about medicine was very limited. Just to think a little bit about the knowledge of that time, consider that toothache was cured with cocaine, the cough was cured with heroin, and the asthma was cured with cigarettes. So this gives you a sense of what they knew at that time about medicine, and why we have to rethink all the processes today in a different way. Also, today we are very much affected by chronic diseases that account for about 80% of the total spend. So we should rethink the whole processes due to all these changes. So what happens when a patient is sick? The first thing that you want to do if you want to rethink the processes is like really putting yourself in the shoes of the patient. When a patient is sick, the first thing that does is the pre-diagnosis. So generally he or she goes online, Google, try to find information. So first of all, actually needs some awareness, right? Then does a self-assessment through Google or other pieces of information. Then it goes to get a diagnosis from the physician, and the physician generally asks for further analysis, tests, scans, or advices from specialists. And then the physician is possibly able to make a diagnosis or send to other specialists. Then there is finally the treatment decision, which is generally a one-size-fits-all treatment. And finally, the treatment administration and the reassessment of the patient. Now, you can understand that in this long and complicated journey, there may be a lot of mistakes. There may be delays, so the patient may not get aware of the disease until later stages. There may be miscommunication. The patient is unable to communicate with the doctor, or the doctor is unable to communicate with the patient or with the other doctors. So there may be misunderstandings. There may be misdiagnosis. Sorry. There may be wrong prescription or dosage miscalculation. You know, every human individual, every human is different in and not only in age and gender. There are so many differences in us, so the one-size-fits-all treatment may not be actually the best one. You may want to have more precise medicine that takes care of the differences between individuals. Then there are also problems in the drug administration. Like the patient can take an overdose, can take the drug in the time where they shouldn't, and can combine the drug with other drugs that were not supposed to be combined, and so on. So at the end of the day, there are so many possible problems, including a failed patient education, which is very important, because then you end up with the patient maybe doing the same mistakes that they did before. And so if we look at the death causes, the death by cause, we were speaking about COVID as a tragedy, but actually if you look at the major causes of death in the US are heart diseases and cancer, that by far passed COVID, and they are not spoken as much as it. If you look a little bit more, you see that the fourth cause after COVID is medical errors. Before COVID, this was the third cause. And we're talking about 251,000 people dying every year due to medical errors. So obviously there's something wrong, and patching it, as we have done so far, is not the best scenario and the best way to address it. In fact, even if we, in the optimistic case that there won't be other pandemics, we are going towards a very important global emergency, which is the demographic emergency. So as fertility is going down and longevity is going up, we are getting, life expectancy is going up, actually. We are getting a problem, a serious problem, that all the countries are getting into to reach a plateau of demographic growth. And this plateau will cause that people, older people, will be more than the younger people. So for example, if you look at people above 65 years old, they are getting more and more, and they tend to pass also the people below 5 years old. Why is this important? Because the people above 65 years old tend to use the 3 to 5 times the services, the healthcare services, that a younger person does. So this will mean more pressure on the healthcare system. And if we look into some projection in 2050, about 30% of the population will be over 60 years old. You can see this projection. So we will have basically a lot of citizens that will need the care of very few citizens. And you can imagine all the consequences of this. So automation is absolutely important, because otherwise we're gonna get not only a lower quality of service, but higher cost, so lower accessibility to the services, and indeed worse outcomes. Another important thing to keep in mind is how much we are spending about our GDP. If you look at all countries, the US is probably the one that is spending the most. It goes between 13 to 17%, depending on the years. But what is incredibly interesting is that all the most developed countries spend about 3 times for healthcare what they spend for education. And you can understand that if you have more educated people, you may actually improve the processes. You can learn more about the healthcare system, medicine, and so on, and you can actually save more people. So actually, we are wasting our money into a bucket that is not giving us anything in the long term. It's only maintaining somehow the current situation. So what we need is automation, so that we can reduce the money invested there, and we can move this money on education and progress. Today we have a very great opportunity, because the advancement of technology, which has followed the Moore's law in the last years, the Moore's law says that some technologies advanced duplicate their power within a certain time period, and at the same time they reduce the cost. So this is offering us a great opportunity. Think a little bit about, for example, the TC, the tomography, the computerized tomography. If you look at this chart, what you can see is the amount of pixel that the computerized tomography was able to capture in 1971, and those that it is able to capture in 2015. You can see it's an exponential growth. So you can see how this growth is consistent. And you can look also on the right side of the chart, you see how faster it became over time. And it's also a logarithmic scale, when you can see here that in the last 45 years, the speed has increased very significantly, such that you need 100 seconds in 1970s, and you need 0.1 second nowadays. Similarly, the Moore's law has been applied to the cost of human genome sequencing. If you look here, only in 2001, the cost of sequencing was $100 million, while today is approximately $1,000, and it's going low by the day. What we can learn from here. We can learn that these technologies are getting faster, they're getting better, they're getting more accurate, but they're opening also new opportunities. So before the genome sequencing was used only for certain purposes, nowadays we can use for other purposes because it's much cheaper and it's much faster, and we can do that. And similarly with all the other technologies. So new applications. The tomography, the computerized tomography can be used almost in real time, while it was not the case before. So let's get a little bit about the framework that was proposed by Eric Topol, and it's the framework of deep medicine. Deep medicine consists, as I said, of 3 major branches, which is deep understanding, deep learning, and deep empathy. So if you think about deep understanding, you can understand it as perceiving, so capturing information from the world. Deep learning is about learning from this data, and deep empathy means like really be humans when you perform the medical profession, medical jobs. As you certainly know, nowadays we have sensor everywhere with the IoT systems, wearables, and so on. Data is now available almost in real time. You know that the big data is described within 3 dimensions, which are called the 3Ds, which is volume, velocity, and variety. So we pass from megabytes to petabytes. We pass from simple tables to video, unstructured data like text, images, and so on, music, audio, and so on. And data velocity, we pass from data that was before it was delivered in batches, then it was delivered in periodically, time to time, and now it's real time. So we are capturing as we speak. And these kind of tools are allowing us to do quite a lot of things and learn a lot of things, also from healthy patients. So we can also compare what happens on healthy patients and what happens on unhealthy patients. So we can learn quite a lot of this from this data. So we may monitor the population and increase the medical knowledge at the same time. I think you are familiar with most of these devices, but they include like smart inhalers that can tell you when you have to inhalate, or the insulin pens. They can tell you how much insulin you need to get if you have diabetes problems. The smart implants that can go under your skin and can help you when you have to recover from a procedure. They can help you because they can monitor all your internal part of the body, like temperature and so on, and tell you whether you need some medicine or you need some rest or whatever you may need to recover faster. And then the brain implants, which is something that is being analyzed, introduced actually very recently for patients who cannot move because they're paralyzed. And these implants allow them to interface with tools, and these tools are generally they can be computers, so they can communicate, or they can be robotic tools that can perform tasks. So these are all the advancements to which we are assisting today. And what we can extract from all these tools? Well, we can have an immediate and fine-grained information about the patients, which can become their clinical history. Like it can generate clinical information that can be used either now or later, and they can be compared with other patients. Another important thing is that the patient doesn't need to stay in the hospital. You don't need to monitor the patients in the hospital. So the healthcare system is moving out of the walls of the hospital, so which are very expensive to maintain and so on. And so there is a home-based care. And as I said before, this is not only saving the information about the single patient, but is also allowing another thing, which is the population healthcare management. So, and when you do population healthcare management, you can predict pandemics, you can mitigate them. For example, here you see the picture of the app that we built with MIT. Is a tracing app that allowed people to be informed if they got in contact with somebody who was positive to COVID. Then, you know, there are like the watches that have been used to predict hotspots by checking the heartbeat. So in some areas, they noticed that whenever there was a higher heartbeat, sleeping heartbeat in some areas, they assumed there was an hotspot. And in many cases, this was actually true. And then sensor can be used also to check the sewers to see whether there are viruses or overutilization of some drugs and so on. But as we were mentioning before, perceiving is not everything. After we perceive, we also need to learn from what we perceive. So data needs to be modeled, sources needs to be combined, pattern needs to be identified, insights need to be inferred, informed decision needs to be taken. So that's exactly the part where deep learning gets into the game, because deep learning allows you to do exactly that, to analyze the data, finding pattern, and this pattern again can go directly to the individual benefit, so early risk prediction, differential diagnosis, treatment optimization, possibly a personalization of the treatment, but it can go also on the population side, like early threat detection, trends and risk factor detection. But that's not all, because once you learn about the individual and when you learn about the population, what you can do is also optimizing the process. And that's the part that we are very interested in, because saving one person, when you can save millions possibly, of course, you want to look in that direction too. So we want to extract data for the single individual, the population, and the processes. But in order to achieve these goals, it's crucial to actually use all the source data. And as of today, most of the data is saved in textual data, textual format actually. And it's about 80% of the medical data is recorded in textual form. And unfortunately is not utilized properly. Why? Because computers until recently were not able to process natural language, and because of that you needed not only to create the medical notes, but you needed an individual, a human, to read those notes to make sense of them. But what a consequence of this is that only those humans that actually read those notes were able to learn something from them. And we, as investigators of medicine, we had a very low resolution picture of the diseases, because we are unable as humans to read quite a lot of textual information. We have to read sequentially, maximum 1,000 words per minute, and we have all the limitations that humans have in this. So that's the picture that you see on the left side is the Mona Lisa, and it's how it's an analogy of how we look at medicine today from a low resolution perspective. But what if we were able to use all this data? Well, we could look at medicine in this way. And definitely you see that understanding, in this case, a painting that is an analogy of the problem may actually help a lot. So natural language processing is a technique that allows you to take advantage of the textual data too. I don't know if you want me to get into technical details about that. I can spend like 5-10 minutes on this and then move on. Is it fine with you?
Sure.
Yes,
Yeah?
please go ahead.
Great. So natural language processing is based on two major concepts: representations and similarity. Representations means that whatever we want to study, whether it's a text, whatever, or something else, we have to represent it in a way that the computer can understand. And generally this way are vectors, tensors, and so on. And the similarity is the fact that according to Quine, there's no entity without identity, meaning that the only way to understand something is to put that something into a context. And to put that something into a context is to look at the similarity with other objects. Okay, so that's how you a computer can learn that one word is similar to another, so it has a similar meaning to the other word. So, and to do so, you have to find the representations that allow you to project whatever you represent into a vector space, like the ones that I'm showing you in this slide. And this vector space should be reasonable for a human too. So here, if you look at this vector space, you can see that, for example, teaching and curriculum are close to each other. You see the teacher and student are somehow close to each other. I mean, educational and education are close to each other. Academic, faculty, and graduate are close to each other, and so on. So this map somehow represents some kind of semantics of these words. What has been found is that if your representation is actually very good, you can perform some analogies. So you, for example, you may derive a new word from mathematical operation, algebraic operations. So for example, you want to find the representation of a queen, you can do king minus man plus woman, and you get the representation of queen. So this is very interesting because with mathematical terms, you can actually find semantics, and you can create a geometry of semantics. So if it works with king and queen, it may work also with capitals. In fact, if you get Spain, you take out Madrid from Spain and you add Rome, it's very likely that the remaining vector will be a representation of Italy, and so on. And you can perform this as much as you want. If we were able to represent in a smart way also sentences, we could perform a similar analogy also on sentences. So that's how actually we can play with meaning. So most of the AI techniques that are used today are supervised ones. Supervised techniques are learning from annotated data, which means data where you have already a combination between input and desired output. You take all this data, you pass it in input to this machine learning, supervised machine learning methods, and they adapt their parameters internally such that they can learn the distribution between the inputs and outputs and learn the mapping between the two. Once they learn this mapping, you can give new data that was not presented during training, and these systems generally are able to generalize to this new data there's the correct mapping. Until about 10 years ago, the major approach were the feature-based machine learning methods, where you had the input. The input was represented by a human that generally coded a software to extract features. Those features were then given in input to the machine learning method that learned the mapping representation till the output. Nowadays, we use neural networks and we use deep learning. In deep learning, you don't have anymore the human extracting the features. Deep learning can actually create the features on its own. So you give the input and the system automatically create the features in the first layer, and then it will learn all the mapping parameters internally before the output. The neural networks are somehow inspired to the biological neural networks in our brain, where we have all those neurons that communicate with each other through axons and dendrites, and the artificial neurons are a simplification of this biological thing. So how does machine learning learn? Well, machine learning learns by a trial and error approach. You can see here in this picture with there are two classes, the blue one and the red one. The system has to learn how to split them. So this line is very wrong now. This is the boundary between the classes. It's very wrong. So because it's very wrong, this line will be moved at every step a little bit closer to the border between the two classes until it will optimize the results. Once it optimizes the results in the training set, you will see that it works also on the test set. Here in the picture on the top, where you see those mountains with different colors, this is called the error, the cost function, basically. So the cost function tells you the amount of error that you have, that the system is producing. So when you are starting your training, the amount of error is on top of the mountain, and the goal is to arrive in the bottom. Not always you arrive at the very bottom. You can arrive at the minimal. It's called a local minimum. You can arrive at a local minimum, which is not exactly the global minimum, but generally is it approximates quite well the global minimum. So at every step, you will see that as the system learns, it goes down from the mountain and try to find the right place there. So let's go a little bit towards what I have contributed to the field. In 2019, if I'm not wrong, or 2020 probably, we wrote this paper with my colleague Nicola Marino and many others, where we had an overview of the systems that can actually support the fight against COVID. We were in the pandemic, in the middle of the pandemic, and this paper was accepted by Nature Digital Medicine. And the points where we focused were risk prediction, continuous monitoring, early diagnosis, treatment development, patient selection, and adverse event detection. And you can see how each of those try to address some of the points that we saw before in the patient journey. So from the prevention, I talked already before about the tracing apps. I don't get very long here because it seems to be almost an outdated topic today. But there was a lot of issues about privacy that needed to be understood at the time when we were developing it with MIT. Instead, it's very crucial to speak about screening and digital biomarkers. Today, this is incredibly important because there are these apps that are able to capture some signals of disease much earlier than humans are able to. In the case of COVID, there were apps that could record your breathing or your voice or your cough, and from there predict whether you were at risk of having COVID. Or there were also surveys-based apps and so on. Today, I can tell you there are some companies that are working in screening for Alzheimer and Parkinson, and these companies are growing incredibly. I wrote some papers with some of them, and these digital biomarkers are becoming a very big thing in predicting this type of diseases that will come later generally in a later age, but you can already see signals longer before. Other possible applications are the optimization of the patient journey. At Cambridge, they studied a system where they could predict with a certain level of accuracy what kind of resources every patient would have needed to recover, or whether the patient couldn't recover at all. They were predicting which patient would have gone to the ICU, which patient would have needed a ventilator, and which patient would have needed a bed in a normal room. And here you see the accuracies were able actually to identify the risk that the patient would have died with 86–87%. ICU admission was about 83%, and ventilators was about 77%. And you can see how having this type of information may help to optimize the utilization of the resources. Then, of course, there are ethical issues that are crucial, like do we want to listen to the computer and then don't provide any resource to this person because the computer has predicted that this person will die? No, of course, there are ethical issues that are bigger than this, but I think we should start thinking about how to optimize these systems, especially in case of extreme pressure on the healthcare, as it happened during COVID. And of course, there will be ethical boards that will decide what is right and what is wrong on that. About the diagnosis, you see that imaging has been incredibly good. Neural networks are impressively accurate in identifying disease through images. They outperform radiologists by far, with significant results, actually. They miss something, of course. Radiologists miss something too. But this means that we can start taking advantage of that. And I can tell you that in many hospitals in the US, this is already the case. For another applications of AI is the drug discovery. So one of the major problem is that developing a new drug has a huge cost, and it takes a lot of time. It costs about $2.6 billion, and it takes over 10 years to get on the market, and 9 out of 10 drugs fail during the clinical trials. So you can imagine what a waste. What we are learning is that it is possible to model these drugs not only in the labs, but also in silico. So through models that can predict the properties of the drugs, and they can do it very fast without big costs, because you don't need to have a specific lab and wait the reaction times and so on. And this is already a big advancement. Drugs are being developed through these models. Generally, approaches that are used is like perturbation of a known drugs reaction and chemical reaction, and study of that. Getting into some projects that I worked on, exactly on December 2020, when the vaccines were delivered in the US, were starting delivering. There was a big issue about vaccination hesitancy. So people were concerned about the vaccination, and we wanted to try to look into this problem, because we wanted to try to understand why they were so hesitant, and we wanted to provide this information to the relevant people that could help educating or anyway create some strategy to reduce and mitigate these concerns, basically, against the vaccination. So we built a system that tried to identify adverse events into tweets, and this system was able to basically, sorry, 1 second, because yes, there you go. This system is here. You can see in this slide, it's on the right side. The system was able to download every day all the tweets that were mentioning keywords related to COVID, and it was extracting information from like the location from which they were published, what kind of hashtag they were used, what kind of concerns people had, for example, whether the tweet was positive or negative in terms of sentiment, what resources the people were reading. So we also look at which website the users that were publishing those tweets were reading through. And finally, we were using this system that was extracting the adverse events. So extracting the adverse events means to find that somebody was complaining about an adverse event, a side effect of the vaccines, and we were looking at the reaction of other users on that. The system was made available. It's still available at this link that you find here. So if you want to look there, it's currently working on all the vaccines. It can be applied to any other drug if there is a need. And it helps you to understand a little bit what people think about those drugs, basically. You can see here one of the module, which is the localization module. You see that this was taken at the very beginning of the pandemic. We were focusing only on English. Now we are focusing on multiple languages. But while we were focusing only on English, you can see that, of course, the tweets were mostly coming from Anglophone countries. We noticed one thing, that in terms of news, people were mostly reading reliable news. So you can see here the top 5 were kind of reliable news. But if you look at the position below the 5th of the 10th, you could see that there were a huge amount of fake news websites that were not the most common ones, but they were that many that if you adapt them all, then you could pass actually the most common, the most reliable website too. And here you see a word cloud, which shows you the adverse events about that the people talk about. If you go on the website, you can click on one of those adverse events. Of course, the size of the word means the frequency. So if you click on one of them, what you see is exactly the tweets that are mentioning it, and you can analyze them. You can look what they are talking about. Here you can see the correlation between the side effects and the given drugs that help to see, for example, the Pfizer was very highly related to allergic reaction, while, for example, AstraZeneca was highly related to a headache. We also, after AstraZeneca was put out of the market, we checked whether there was a signal that people was having all these cardiovascular issues due to that. And we actually found a lot of those complaints in Twitter. So what it means is that we were unable to capture this signal, but the signal was there. So meaning that the tool is actually usable for the future. I think I have two more use cases. I go very quick through them, but this one was with MIT and MGH, Massachusetts General Hospital. What we found is that the decisions, all the clinical decisions are taken on the base of the experiments and the clinical trials done on 3% of the population, meaning that from this 3%, then the remaining 97% will get what has been learned on the 3%. So getting back to our discussion about how to extract information from clinical notes, we had these clinical notes you can see on the left, and we wanted to structure it into a binary attributes. In this case, we were working on breast cancer reports. So we want to see which breast the problem was, which kind of cancer it was identified, whether it was identified or not, and so on. Structuring this data helps to the doctors to make analysis, which can be retrospective analysis for writing a paper, or which can be also finding similar cases to try to suggest similar, for example, treatments. So you can imagine the importance of this work. We collected data from many hospitals in Boston, and we built neural networks, a convolutional neural network, which got an input, the pathology report. It represented it. Before I was talking about representation. In this case, it represented it to a tensor. Then the neural network made all the decision and return a confidence score about whether something was found, like cancer or what type of cancer and so on. And this was then put into a table like the one that you saw before. The system was performing pretty well. It was getting an accuracy above 95%, and in some cases above 96%. It was working well both on the institutions on which it was trained and the institutions on which it was not trained. So there were also cases in which some institutions were kept out of the training set to see whether the system was able to generalize. And then finally, this thanks to this tool, we could write papers where we analyze 6,000 cases, while the average number of cases that are analyzed in most papers is about 300 to 500, 600. So you can understand how much more detailed the picture, high resolution is the picture of a researcher in MGH compared to a researcher elsewhere in the world. This system was applied to many types of cancer, including many organs like brain, lung, pancreas, prostate, and so on. Finally, another thing that we did was predicting the patient benefit for a very highly risky and expensive procedure, which is called CRT, cardio resynchronization therapy. Basically, 1/3 of the patients that undergo this procedure don't make it. Generally, they don't benefit, and the part of them even die due to the complication of the procedure. So we were looking into that. We wanted to identify those patients before they went through the procedure. And we built a system, and the system was actually able to identify about 25%, those pink ones, 25% of those patients that wouldn't have benefited of it. So it wouldn't save all of them, but it would have reduced the damage that sending some patients that wouldn't benefit of it would have caused. And getting to the last section of the presentation is the deep empathy. Deep empathy means to bring the doctors to be doctors, not bureaucrats. So not writing notes the whole time, but actually speaking with the patient. Several surveys demonstrated that the patients tend to be rude, busy, nervous, condescending, and so on, because they are actually very busy and stressed because they have to write notes. During the 15 minutes visit, in most cases, those doctors haven't seen the notes of the patient, but they are writing the notes for the patient, and they're writing, and it seems that at most those doctors look at the patient, they have eye contact for maximum 2-3 minutes. This has a very deep consequence also in the psychology of the healthcare of the patient. So you see this funny comic that shows that the doctor is very worried about cholesterol, while obviously the patient has another problem. And this brings us to reasoning about the reason of deep empathy. The secret of caring for the patient is to care for the patient, Peabody said. And this means to listen, to understand, to engage, to instruct, to educate. As Hippocrates said over 2,500 years ago, it is often more important to know what sort of patient has a disease than what sort of the disease a patient has. So starting from this, we may want to actually consider this when we will re-study the processes of healthcare. To summarize everything before closing, is population is aging and is getting the healthcare system is getting structurally vulnerable, and we need to make it sustainable. Deep medicine promise to be a good way to achieve that. There are, of course, obstacles, for example, the interpretability of the models, the fairness, there are ethical issues, there are problems with the insurance that can take advantage of this data for their benefits. There are other companies that can consider this for their business rather than for the patient's health. So what we need is healthcare professionals that will coordinate and with the regulators and will work out a path that is focused on the patient benefit, because the patient benefit is the society benefit as a whole. And with this, I close it, and thanks a lot for listening. I'm open to a chat with you. Thanks a lot. I hope I didn't go too long.
Thank you. And just any questions?
Yeah, I had a question. So with this deep medicine, how do you feel like doctors' responses have been with machine learning and diagnoses with their patients? I mean, do you feel like there's like a level of control that they still want to have?
Yeah, there is definitely a level of control that they want and they need to have, because there is an accountability issue. I mean, it's a very complex topic in the sense that doctors, there have been studies, and doctors either agree with the machine and so they feel a little bit less accountable, or if they disagree with the machine, their accountability will grow pretty much. And this will the consequence of this is that doctors may just agree with the machine because they don't want trouble. You see how this may be problematic. So I think we have to rethink everything in this new perspective, and we have to see which models are working, whether we can interpret why the model has made a certain prediction rather than another, and maybe there's where the doctor may be more comfortable to agree or disagree with the machine. But that's also an engineer problem. It's not not only on the doctor side.
May I make a comment?
Absolutely.
Okay, I actually involved in a project, and to me, the best way to get the doctor to trust the process is to get them involved. And the project that I'm involved actually started with their academics, but also involved, in this case, are ophthalmologists. And the whole thing has been progressing very well because they are actually a key component of the process, and they are actually helping in training the network.
Yeah, I totally agree. Like most of our work with Dana-Farber and MGH, we had the surgeons that were actually responsible of the project, and they actually are using our tools in the background. They don't use it in production, but they look at them when they have time and they try to understand. Yes, so I absolutely agree.
I had a question, Julia, if I could. So John Newsom, great to meet you, Enrico, and really enjoyed your presentation. My question was more about your current place of work and the degree to which ML and AI techniques are accepted, and and the degree to which their potential benefit relative to product development is accepted. I'm presuming that you're on the kind of the pharmaceutical side of bio rather than the consumer healthcare side, but maybe you can comment on, the degree to which ML and AI techniques are viewed within bio as being of strategic importance.
Thanks for the question. Yeah, so I work in pharmacovigilance. So pharmacovigilance will take care of anything that happens after the drug is in the market, and the medical affairs also. So clinical trials that are made after the product is already in the market. What we do is trying to process all the data we will receive. We receive a lot of medical notes, we receive a lot of adverse event reports and so on. And for us, there's the regulators require us to analyze all this data. And before, this was done manually. So we had a big amount of people that were reading these notes daily and writing reports and so on. Now we are trying to provide machine learning based systems that can help them in this analysis. That's basically my responsibility at Bayer. And recently we tried to put the human in the loop, because as Jose mentioned before, Dr. Casillo, the human in the loop helps people to feel they are participating to something rather than get it passively. So that's it. I honestly am not very confident in the product development. I know that we are using also AI a lot for the supply chain and for marketing and so on. Yeah.
That's great. Thank you.
Thanks.
We have time for one more question, and then we're going to thank Enrico for his presentation. Any other question?
I have a question, Mark Flieger. Yes, so you mentioned digital biomarkers, which are relatively inexpensive, but you also talked about imaging, which might require somebody to go somewhere. So can the digital biomarkers be used to sort of stratify individuals and say, oh, well, based on this digital biomarker, I think you ought to go somewhere and get a scan of some sort that's much more expensive?
That's an incredible question. Thank you for making it. So in the books that Eric Topol wrote, he spoke also about these campaigns about screening, right? This huge campaign about mammograms and about other things. And it seems, I'm not an expert on the side, so please take my comment with a grain of salt, but apparently it seems that these campaigns are not actually very beneficial because they are huge. They spend a lot of money. I'm not referring particularly, I think the prostate, he was referring particularly to prostate cancer. Like every, I don't remember now the statistics, I don't want to say something wrong, but many men, like a large majority of men will have prostate cancer at a certain point in their life. But this doesn't mean that the prostate cancer will kill them. It can be a very neutral cancer that is not going to affect their life anyhow. But these screenings will find all of this, and actually damage of trying to treat a cancer that will never treat them in a certain sense, maybe worse. So yes, definitely we need a stratification with screenings and see whether going farther and farther depending on the seriousness of the issues.
Thank you.
Okay, we are at time. Jose, do you want to say some closing words?
Well, I just want to thank you, Enrico, for a wonderful presentation, and we hope to interact with you in the future.
Thanks.
Absolutely. Thanks, Enrico, from all of us. And it was really nice. Thank you for the presentation. A very kind of hot topic these days.
Yes, and thank you very much, everybody, for coming, and have a wonderful weekend.
Yes,
Thank you very
long
much. Really
weekend.
appreciate it.